All right, welcome back, everybody. So this week we're happy to have Colin McSwiggen, who will tell us about cousins and ancestors of the arithmetic-geometric inequality.
Good morning, everyone, and yeah, thanks for inviting me to speak in the seminar. Since this is a representation theory seminar, I want to warn you all at the very beginning, this talk will not contain very much actual representation theory. It will contain a little bit, but it's talk mainly about special functions, and in particular about majorization inequalities, which are a type of inequality that many different families of special functions turn out to satisfy. However, essentially all of the functions that I'll talk about today, so symmetric polynomials, hypergeometric functions, spherical functions, have some kind of representation theoretic interpretation, and I will discuss that a little bit. I'll start with something really basic, which I imagine most of you have seen before, the arithmetic-geometric inequality. Namely, given two non-negative real numbers, it is a fact that their arithmetic mean is at least as large as their geometric mean. This is a fact that mathematicians have been aware of for a very long time. It's been known for at least 1600 years. I think it was, as far as we know, first written down by Pappus of Alexandria in the 4th century. And it is one of, I would argue, the most widely used mathematical facts still today. If you look at this inequality, it's not too hard to convince yourself that this statement is actually equivalent to the convexity of the exponential function. More generally, if you have a collection of n non-negative real numbers, their arithmetic mean is also at least as large as their geometric mean. And you'll notice that if you raise each side of this equation to the nth power, what you get is an inequality between two symmetric polynomials. Now, the arithmetic-geometric inequality is not the only member of its species. It has a large family, which are called symmetric mean inequalities, which have attracted increased interest from combinatorialists in recent years. And in particular, today we're going to be looking at majorization inequalities, which are kind of a big class among these symmetric mean inequalities. I'm going to talk about how many of these inequalities can be unified via a fundamental theorem that gives a kind of monotonicity property for spherical functions on symmetric spaces. Spherical functions are sort of the basic waves that are used in harmonic analysis in symmetric spaces. So they play the role that, say, sines or cosines or exponential functions play in ordinary Fourier analysis. And if I have time at the end, I will also talk about an even more general monotonicity conjecture for Heckman-Opdam hypergeometric functions, which would sort of unify and also generalize the case of the inequalities for spherical functions, and would give a further of inequalities for symmetric polynomials as well. So in the first part of the talk, I'm going to talk about a preorder on vectors known as the majorization order, which turns out to control a bunch of inequalities between symmetric polynomials. In the second part, I will talk about a generalization of this notion of majorization and show how it controls inequalities for spherical functions. The second part of the talk will assume some background on Lie theory. So for instance, I'm not going to define what a root space is or what a root system is, but I won't assume any knowledge about symmetric spaces in particular. I'll try to give a very short crash course on all of the actual required symmetric space theory within the talk. And in the third part, I will talk about a still outstanding conjecture on Heckman-Opdam hypergeometric functions, which are kind of a generalization of spherical functions, which would kind of unify all the results that I'm going to present. So to begin with, let's talk about Young diagrams. Again, in a room full of representation theorists, I don't imagine that I need to tell everyone what a Young diagram is, but just to fix some conventions, a Young diagram is a diagrammatic depiction of an unordered integer partition as an array of boxes arranged in rows of weakly decreasing length. So here we have two Young diagrams that are both representing partitions of 8. Equivalently, we can think of a Young diagram as a vector with weakly decreasing non-negative integer coordinates. And we'll use the absolute value notation to just indicate the total number of boxes, which if we think of it as a vector, is just the sum of the coordinates. So it's not the length of the vector. There is a partial order on Young diagrams called the majorization order. So given two Young diagrams, each with n rows, lambda and mu, we say that lambda majorizes mu, which we write with this curly greater than or equal sign, if first of all, lambda and mu both have the same number of boxes. And second, if for all k from 1 to n, the number of boxes in the first k rows of lambda is at least as large as the number of boxes in the first k rows of mu. But note that there's nothing in this definition. If we think about lambda and mu as being vectors with non-negative integer coordinates, there's nothing in this definition that actually requires that the coordinates of those vectors be non-negative integers. So in fact, these two parts of the definition actually define a partial order on all vectors in Rn whose coordinates are weakly decreasing, and this partial order extends symmetrically to a preorder on the entire space Rn. It's a preorder, not a partial order, because you can have because you sort of don't have this. You can have 2 points that are in the same Weyl orbit that are not equal, but that both majorize each other. So we don't get a partial order unless we restrict to some chamber of the action of the symmetric group. But given x and y in Rn, we say that x majorizes y if x down arrow majorizes y down arrow, where x down arrow and y down arrow are obtained from x and y by sorting the coordinates in non-increasing order. So that's one definition of so an example. Here we have the two Young diagrams that we saw before. Indeed, here lambda does majorize mu, and to check that, we just count that they both have 8 total boxes, and then looking from the first row down to the fourth row, in each of the first k rows, lambda has at least as many boxes as mu does. So that's one definition. It turns out that there are a lot of other equivalent definitions of majorization. So recall that a matrix is an n by n matrix is doubly stochastic if it has non-negative real entries, and if all of its rows and all of its columns sum to 1. And it turns out that x for 2 points x and y in Rn, x majorizes y if and only if y is the image of x under multiplication by a doubly stochastic matrix. A third equivalent characterization is that x majorizes y if and only if y lies in the convex hull of the orbit of x under the action of the symmetric group on Rn permuting the coordinates. This convex hull is a convex polytope called the permutahedron of x. Permutahedra are an important family of polytopes that have been intensively studied in combinatorics. This third definition is going to be the most important one for our purposes, because later on, when we want to generalize the majorization order, we'll be looking at vector spaces that carry an action of some group other than Sn. And in that case, the most straightforward way to generalize the concept is to look at convex hulls of the orbit of some point under the action of this other group. So we've seen these three definitions, but actually there are many, many more ways to characterize majorization. And in some sense, basically all the results that I'm going to present during this talk are further characterizations of the majorization order or its generalizations in terms of the pointwise values of various symmetric functions. So just to make sure that the permutahedron idea is clear, this is the permutahedron of the point 321. The other vectors in R3 that are majorized by 321 are just all of the points of this hexagon, including its edges and its vertices. And note that even though we're in R3, we do have a two-dimensional hexagon rather than some three-dimensional polytope, for the reason that all of these vectors have the same trace, right? Every point in this hexagon has coordinates that sum to 6, and that just corresponds to the requirement that in order for one Young diagram to majorize another Young diagram, they have to have the same number of boxes, right? It's just this linear constraint that restricts you to this particular affine hyperplane. All right, so that's all for now about majorization. Are there any questions so far? All right, so I'll go back to the arithmetic geometric inequality. There is a significant generalization of the arithmetic geometric inequality due to the Scottish guy, Rob Muirhead, around the turn of the 20th century. For any vector A in Rn, which could be any vector, so its coordinates could be negative, they could be irrational. The A mean of a collection of real numbers x1 through xn is defined by this formula. That is, we just take the normalized sum over sigma and the symmetric group of the product of each xi raised to a sigma I. So as examples, it's pretty easy to see that if we just let A be the vector 1 followed by a bunch of zeros, then we get the arithmetic mean. If we let A be the vector 1 over n in every coordinate, then we get the geometric mean. And what Muirhead showed is that for two vectors A and B in Rn, A majorizes B if and only if the A mean of every collection of positive real variables is at least as large as the B mean of that same collection of numbers. Now, here we've assumed that x1 through xn are all positive. This is just kind of a technical assumption because we allow the A's to be negative, right? But if we have non-negative A's and non-negative B's, then it's pretty easy to see that just by continuity, we could let x1 through xn be any non-negative numbers. Now, it's also clear that the A means and the B means in this theorem are symmetric under permutation of the xi's, just by construction, right? So we can reinterpret this result in terms of some standard symmetric polynomials in the case where we take the A's and B's to be all non-negative integers. Namely, these are, right, the monomial symmetric polynomials. So if we let lambda be some Young diagram and think of it as a vector, then the lambda mean of the variables of x1 through xn is just the normalized monomial symmetric polynomial, where the normalized monomial symmetric polynomial is obtained by starting with the standard definition given here in the formula and dividing by the value of the monomial symmetric polynomial just at all ones, which is just equal to its number of terms. Oh, are you able to see my cursor, by the way? You are. Okay, great. So Muirhead also gives us this inequality for the monomial symmetric polynomials. That is, lambda majorizes mu if and only if this normalized monomial symmetric polynomial associated to lambda is greater than or equal to the monomial symmetric polynomial associated to mu after normalization at every point with all non-negative coordinates. Now, it turns out that similar inequalities for other types of symmetric polynomials have been known and studied for centuries. But the fact that all of these inequalities are similar is not obvious. And the reason that they're not obvious is because people didn't think about them in terms of this framework of majorization. So let's look at some of these other types of symmetric polynomials. We have the elementary symmetric polynomials. So the kth elementary symmetric polynomial is just taken in n variables, is obtained by taking the sum of all degree k monomials in n variables, such that each variable occurs in each term with degree at most 1. Given a Young diagram, we can define the elementary symmetric polynomial E lambda as just the product of the E lambda i's, where the lambda i's are the number of boxes in each row. And similarly to the monomial case, we can define the normalized elementary symmetric polynomials by just dividing by the number of terms. Likewise, we have the complete homogeneous symmetric polynomials, which are defined exactly analogously to the elementary symmetric polynomials, except we drop the requirement that in each term, a given variable can occur with degree at most 1. So we just take the sum over all degree k monomials in n variables. And analogously, we can define the h lambdas given a Young diagram and also the normalized complete homogeneous symmetric polynomials. Now, the E lambdas and the H lambdas are both well known to be algebraic bases of the ring of symmetric polynomials in n variables. So we have various inequalities that relate different normalized elementary and complete homogeneous symmetric polynomials to each other. So here are three examples dating back to the early 18th century due to Maclaurin, Newton, Schur, and there are plenty of other examples due to other people. About 10 years ago, three combinatorialists, Cutler, Green, and Scandera, made a systematic study of inequalities of this type. So they studied these and many more inequalities, and they effectively generalized all of them. And the results that they proved are all majorization inequalities. That is, the inequalities between the pointwise values of the symmetric polynomials are all controlled by the majorization order on Young diagrams or by some extension of it. And so all of these inequalities are special cases of results that they show. Now we've talked about the elementary and complete homogeneous symmetric polynomials. If you ask most representation theorists what their favorite basis of the ring of symmetric polynomials is, they will say the Schur polynomials, because these express the characters of the irreducible polynomial representations of GLN. Cutler, Green, and Scandera conjectured and partially proved an analogous inequality for Schur polynomials. The proof was later completed by Straw about 5 years ago, and alternate proofs were given by Apoorvekar and Terry Tao, and also by Ahadu and Mazur. The statement is exactly analogous to the monomial version of Muirhead's inequality, namely, given two Young diagrams, lambda and mu with n rows, lambda majorizes mu if and only if the normalized Schur polynomial associated to lambda is at least as large as the normalized Schur polynomial associated to mu at every point in Rn with all non-negative coordinates. Now, I want you to try to remember this statement because we are going to see it again in a seemingly different context later on in the talk. All right, are there any questions so far? All right, so if not, then I'd like to step back for a moment.
I could ask.
Yeah.
Yeah, is there any geometric meaning of this Schur polynomial?
Geometric meaning?
Yeah, or something. I mean, where does it come from?
Well, I mean, well, there are a lot of different ways to think about Schur polynomials. So, one way that you can think of them like geometrically in a sense is that they are they are the spherical functions on the unitary group regarded as a symmetric space in a certain way. There's also kind of an connection to like cohomology of flag varieties and like Schubert calculus. So yeah, I think there are a bunch of geometric interpretations, although I don't feel super confident talking about them because I'm not an algebraic geometer. I don't know if that's the type of answer that you were looking for.
No, I mean the determinant, is it computing some volume or something?
I see. So like directly from the formula, there very well may be, but I don't. I wouldn't be able to tell you off the top of my head. If someone else has an interpretation of that type that they know, feel free to jump in.
I mean, I cannot. I mean, sorry, I can't imagine exactly. Let's say take an example. What form this matrix looks like actually. I mean, this formula is a little bit not easy to grasp. That's all. I mean, even algebraically. Never mind. Let's go on. I mean.
All right.
Okay. Sorry.
Okay, so if that's all right, then I'll step back for a moment and talk about zoology. So at some point a long time ago, biologists figured out that monkeys and rabbits both have hair. And they also figured out that monkeys and rabbits and frogs all have 4 legs. And a long time after that, they realized that these similarities between these otherwise very different seeming species were an indication that at some point in the past, all of these animals had a common ancestor. Now, at this point, by Muirhead, Colin, and others, we know that lots of standard bases of the ring of symmetric functions, including, the monomials, elementaries, power sums, complete homogeneous, shear polynomials, all satisfy some kind of majorization inequality or other. So as mathematicians, we should wonder, are these all just special cases of some more general principle? And the goal of the rest of this talk is to convince you that the answer to this question is yes. Now, as a disclaimer, I don't yet actually know the full answer in the sense that we don't yet have a theorem that can unify all of the known majorization inequalities for symmetric polynomials. But we can unite many of them. So one way to think of it is that we can kind of trace this taxonomical tree back to the point of animals that have 4 limbs, but not yet back to the point of all vertebrates. So I'll only give you a partial answer. But in order to tell you that answer, I will have to take a detour into the theory of symmetric spaces. So we'll start with the basic definitions. If G is a connected Lie group and K in G is a compact subgroup that is the fixed point set of an involutive automorphism of G, that is an automorphism that is its own inverse. So the orbit of every point under the action of this automorphism has exactly 2 points or 1 point. Then we call GK a symmetric pair. And for our purposes, the definition of a symmetric space will be a manifold of the form G mod K, where we quotient by K from the right. Now, note that K is not necessarily a normal subgroup of G. So X does not necessarily inherit a well-defined multiplication operation from G. That is, it's not in general going to be a Lie group, but it will be a manifold. And indeed, G still acts on it, right? We quotient it by K from the right, but X still carries a G action from the left. And we want to remember this G action. So we are going to consider the pair GK as part of the defining data of the symmetric space, because we'll often be interested in studying K invariant structures on X. So we want to remember more than just the underlying manifold. Indeed, there will often be ways to realize the same underlying manifold in multiple different ways as a symmetric space by taking different groups G and K, and we will regard those as different symmetric spaces. Now, if G is non-compact and semi-simple with finite center and K is a maximal compact subgroup, we will say that X is of non-compact type. This is a confusing term. I don't like it because there are non-compact symmetric spaces that are not of non-compact type. However, this term is now standard in the literature, so I'm going to use it. Symmetric spaces admit a kind of irreducible decomposition. If X cannot be written as a non-trivial product of symmetric spaces, we will say that it is irreducible. And if X is simply connected and irreducible, then it is exactly one of the following, either compact or a Euclidean space or of non-compact type. And for the purpose of classification, generally we can always assume that we're working with something simply connected because the universal cover of a symmetric space is also a symmetric space, and it's pretty easy to classify the possible quotients. So the assumption of simply connectedness is not really consequential. Now note that a simply connected irreducible symmetric space also happens to have constant curvature. So these 3 types correspond to the cases of something positively curved, something flat, and something negatively curved. So when I'm in one of these 3 cases specifically, instead of just writing X, I'll often write X plus, X0, or X minus related to the curvature so that you know which case I'm talking about. So here are some examples of symmetric spaces. The Euclidean space Rn, it already is a Lie group, and we can regard it as a symmetric space simply by quotienting out by the identity. Or by the trivial subgroup. We can also construct it as a symmetric space in a different way by taking the semi-direct product with SON, which just acts on Rn here by rotations in the usual way, and then quotienting out the SON factor. So here is an example of a case where we have the same underlying manifold, but as a symmetric space, these are going to be very different. We can construct spheres as symmetric spaces by taking SON and then quotienting out SON minus 1. Likewise, the space of symmetric positive definite matrices. is a symmetric space, as are compact Lie groups, as well as projective spaces, hyperbolic spaces, compact Lie algebras, and many more important manifolds. Now, notice what I've written here for the compact Lie groups. We could have made G into a symmetric space, again, by just quotienting out the trivial subgroup. But what I've done here is I've instead taken G cross G and quotiented out by the diagonal subgroup, which is often what we'll want to do when we regard a compact group as a symmetric space. This will make a little bit more sense when I get to talking about harmonic analysis on symmetric spaces. If I just quotient out by the trivial subgroup, then I'm trying to do harmonic analysis kind of all functions on G. But if I start with G squared and then quotient out the diagonal subgroup, so the diagonal subgroup is my subgroup K, then when I look at K invariant functions on the group, what I'm really looking at are class functions. So that's how you do kind of harmonic analysis with class functions. Speaking of harmonic analysis, spherical functions are going to be our main tools in doing that. A spherical function is any complex valued smooth function on the symmetric space X, satisfying three properties. First of all, it should be normalized such that its value at the residue of the identity is 1. It should be K invariant under the action of K on X from the left. And third, it should be a joint eigenfunction for all G invariant differential operators on X. So another way to think of this third property is that the spherical functions simultaneously diagonalize the algebra of all G invariant differential operators on X. These are sort of the fundamental building blocks for harmonic analysis on symmetric spaces, in the sense that there is an analog, or really a generalization, of the Fourier transform on Euclidean space called the spherical Fourier transform, or the Harish Chandra transform, which allows us to decompose any appropriate, say L2 or Schwartz K invariant function on our symmetric space in terms of spherical functions. But it also turns out that many important families of special functions that are not a priori or obviously related to harmonic analysis can be realized as spherical functions on some symmetric space or others. So here are some examples. It turns out that if we regard the Euclidean space Rn as just Rn mod the trivial subgroup, then the spherical functions that we get are the exponentials. So in this case, spherical Fourier analysis really just is ordinary Fourier analysis. On the other hand, if we construct Rn by first taking this semidirect product with SON and then quotienting out SON, then we're doing radial Fourier analysis. And in this case, the spherical functions that we get are classical Bessel functions. These are the modified Bessel functions of the second kind with parameter n-2 over 2. Or maybe the first kind. I don't remember. Classical modified Bessel functions. Likewise, with this realization of a sphere as a symmetric space, the spherical functions are zonal spherical harmonics. And if we use this realization of a compact Lie group as G squared mod the diagonal subgroup, then the spherical functions that we get are precisely the normalized characters of the irreducible representations of G. Now, it turns out that the spherical functions on any symmetric space satisfy a majorization inequality that is analogous to Muirhead's inequality. But the ordinary definition of majorization that before is not quite going to cut it. We need a more general notion of majorization. So given a Euclidean space V and a crystallographic root system phi in V, we will write a capital W for the Weil group generated by reflections in the hyperplanes orthogonal to the roots. And for two vectors lambda and mu and v, we can then say that lambda W majorizes mu, which we'll write with the same notation, if mu lies in the convex hull of the W orbit of lambda. Now note that if we take phi to be an-1 embedded in the usual way in Rn, this just recovers the usual notion of majorization from before. Now, in order for this to be useful for studying spherical functions, we will need some way to associate a root system to a symmetric space, but there's a standard way of doing this. It's just the restricted root system. So for now, I'm only going to consider the case of a symmetric space of non-compact type, because this is kind of prototypical. So here I'm going to write x minus. If x minus is a symmetric space of non-compact type, we can take the Iwasawa decomposition of this group G and of the Lie algebra of G. So here, this fractor K is the Lie algebra of K. Fractor A is a maximal abelian subalgebra and the orthogonal complement of K under the Killing form, and N is a nilpotent subalgebra. Then our Killing form on the algebra of G gives an inner product on fractor A. And for any point alpha in that vector space, we will define the root space G alpha to just be the space of all joint eigenvectors of these operators taking the Lie bracket with all H in A, with eigenvalue given by alpha dot H. So the restricted root system phi of x minus consists of all non-zero alpha in A, for which this root space G alpha is non-trivial. Now I've called this the restricted root system. Note that this definition of the root space is basically the same as the ordinary definition for a root space of the algebra G, but I've kind of restricted this requirement of simultaneous diagonalization to hold just for H that lie in A rather than all H in some Cartan subalgebra. Again, we'll write capital W for the Weil group of this restricted root system, and we can then talk about W majorization for points lambda and mu in A. So back to spherical functions. In the case of the non-compact type, there is a convenient integral formula for the spherical functions, which also gives us a classification of spherical functions. So we'll fix a choice phi plus of positive roots. And for any alpha and phi, we will write m alpha for the dimension of the corresponding root space, which is called the multiplicity of the root alpha. And we'll write rho for half the sum of the positive roots weighted by their multiplicities. Then for any little g in the group G, we will write A of G for the unique element of A such that little g lies in a double coset of the exponential of little a of G under the Iwasawa decomposition. So to unpack this a little bit, we can write little g in some unique way as the product of something in big N, something in big A, something in K. Because the group A is a split torus, its exponential map from its algebra onto it is a bijection. And so this little a is just the unique element of the algebra that hits the A part of the Iwasawa decomposition of G under the exponential map. And finally, we'll write dk for the normalized Haar measure on K. We then have this theorem due to Harish Chandra from the 50s. The spherical functions on x minus are exactly the functions, which we'll write phi minus, of this form. So phi minus of lambda is given by this particular integral over K. As lambda ranges over the complexification of A. But two functions of this form are actually equal to each other if the lambdas that index them belong to the same Weil orbit. So what we find is that the distinct spherical functions on x minus are indexed by points of some Weil chamber in the complexification of A. So now I can state what's kind of the main result of this section of the talk, which is that if x minus is a Riemannian symmetric space of non-compact type, then for any lambda and mu in fractor A, lambda majorizes or W majorizes mu if and only if phi minus I lambda is greater than or equal to phi minus I mu at all points of x minus. Now, why are we multiplying by I here in front of lambda and mu? This is basically just a matter of notational convention. If we look back at this Harish Chandra integral formula, what we find is that we need to take lambda and mu with imaginary coordinates in order for us to get a real valued function. So that's just kind of a matter of how the notation works in order for us to get functions for which such an inequality could make sense in the first place. Now, in the interest of time, I'm not going to dwell on the proof here or talk about details. I'm also not going to say very much about the inequalities for the Euclidean and the compact cases. I'm just going to sketch sort of how this also gives you inequalities for the other two types. And the answer is basically that every simply connected irreducible symmetric space of Euclidean or compact type can be constructed from a symmetric space of non-compact type in a canonical way, such that you can write the spherical functions on the Euclidean or compact symmetric space in terms of the spherical functions on the space of non-compact type that you got it from. So starting with some space x minus of non-compact type, we can construct a compact symmetric space x plus, basically by replacing the group G with its compact real form G plus. We can also construct a Euclidean symmetric space basically by taking a kind of deformation of the metric on x minus, where we take a limit that sends the curvature to 0. So the upshot here is that the majorization inequality for the non-compact type almost immediately gives analogous results for the compact and Euclidean types. So for the Euclidean type, we can get all of the spherical functions just by taking a limit of that Harish Chandra formula, and then by kind of like doing the limit inside the proof of the other inequality, we get an analogous inequality for the spherical functions t lambda 0. Similarly, for the compact type, we get all of the spherical functions on the compact symmetric space by considering just the spherical functions. So first of all, we take the spherical functions on x minus, we lift them to k invariant functions on the group G, and we say, okay, which ones of these admit analytic continuations to the complexification of G? We take just those ones, and we then just restrict them to the compact real form and quotient by k again to get all the spherical functions on x plus. So in this case, we find that actually the spherical functions are indexed by some discrete set in the Weyl chamber rather than by the entire Weyl chamber. And the reason for this is that the compactness of x plus basically presents a topological obstruction. It's the same reason that you have only discretely many sines and cosines that show up in Fourier analysis on the circle, where you have a continuous family of exponential functions that show up in Fourier analysis on the line. That's the most basic example of this phenomenon. And then in this case, also just sort of by considering the values of the spherical functions on the original group G, we obtain an inequality for the spherical functions on the compact symmetric spaces also. And it turns out that this allows us to deduce this inequality of Cutler, Green, and Scandera and Sra as a special case. That is, if we realize the unitary group as a compact symmetric space by taking u squared and then quotienting at the diagonal subgroup, the spherical functions are just the normalized characters, as we talked about. We can do this exponential change of variables that lets us write those characters as Schur polynomials, and the Cutler, Green, Scandera, Sra inequality just falls out. But it turns out that Schur polynomials are not unique in this regard. In fact, every compact symmetric space also gives rise to an associated orthogonal basis of the space of W invariant polynomials on A via an analogous exponential change of variables. So in all such cases, the polynomials satisfy a majorization inequality. And so this immediately gives us analogous inequalities for other families of orthogonal polynomials that arise from symmetric spaces via the same mechanism, such as the real and quaternionic zonal polynomials. All right, so to recap what we've seen so far, spherical functions on any symmetric space satisfy majorization inequalities. This recovers some known results like this inequality for Schur polynomials and also implies new ones. In this last section, I'm going to talk about a conjecture which, if true, would unify and dramatically extend almost all of the majorization inequalities that I've discussed in this talk so far. And it involves a very large and versatile family of special functions called Heckman-Opdam hypergeometric functions. So these functions are a multivariable generalization of the Gauss hypergeometric function 2f1. And they interpolate between the spherical functions on different symmetric spaces of non-compact type that all have the same restricted root system. There are also analogous objects that interpolate between the spherical functions for the Euclidean and the compact types. They're called generalized Bessel functions and Heckman-Opdam polynomials. Now, if we were able to show a majorization inequality for Heckman-Opdam hypergeometric functions, it would immediately imply analogous results for generalized Bessel functions and Heckman-Opdam polynomials as well, via the same sort of duality or deformation argument that that we used to deduce the compact and Euclidean inequalities from the inequality from compacting. Now, unfortunately, the Heckman-Opdam hypergeometric function is pretty cumbersome to define. I am going to tell you the full definition, but it's going to take me 3 slides. And even then, I'll be moving pretty fast. So for those of you who aren't familiar with these functions, don't worry too much if you don't catch all of this. The important thing to remember is just that the Heckman-Opdam hypergeometric functions are a family of special functions that generalize spherical functions and interpolate between them. So the setup, we will need a R-dimensional Euclidean space V with this inner product, and we will need a crystallographic root system phi that spans V. We will fix a choice phi plus of positive roots. We'll write S alpha for the reflection through the hyperplane that is normal to the root alpha. And again, we'll write a capital W for the Weyl group generated by these reflections. We'll write Fk lambda for the Heckman-Opdam hypergeometric function. It depends on a point lambda in the complexification of V, and also on this thing K, which is called a multiplicity parameter. It is just a complex valued function from the roots. So it's a function from the roots to C that is constant on Weyl orbits. Fk lambda is going to be defined in terms of solutions to a system of differential difference equations involving these operators called the Cherednik operators. So we'll write rho with the superscript k for half the sum of the positive roots weighted by the value of the function k at each root. And then for any y in the space V, we can define the Cherednik operator dky by this formula. So here dy is just the ordinary directional derivative in the direction of y. So this is just grad f dot y. This over here is just the inner product of y with this vector rho k. So this is just a constant multiple of the function f. This is the difference part of the operator. Here we're taking a sum over all the positive roots of this prefactor times the difference between f and its reflection through the hyperplane normal to alpha. All right. So when all values of k are non-negative real numbers, and in fact, when they're generic complex numbers, but here we'll just consider the case where they're non-negative and real, and then for any lambda in the complexification of V, there is a unique smooth function gk lambda on V, which is a joint eigenfunction of all of the Cherednik operators dky with eigenvalue given by y dot lambda, and which is also normalized such that its value at the origin is 1. The Heckman-Opdam hypergeometric function, Fk lambda, is then just defined to be the symmetrization of the function gk lambda over the orbits of the Weyl group. So we just divide by the order of the Weyl group, sum over all elements, little w of gk lambda of w of x. And that gives us the Heckman-Opdam hypergeometric function. Okay, so that was the definition.
Sorry, Colin, can I ask a question? So the
Yeah.
Schur functions are a specialization of these things, or?
The Schur polynomials are a specialization of the Heckman-Opdam the Heckman-Opdam polynomials, which can be obtained as a specialization of this thing in a sense. So here we're just regarding this as a function on the vector space V, but it turns out that you can analytically continue it to the complexification of V, and if you give it the right complex arguments, then you can get the Schur functions as a special case. Or rather, yeah, I mean, it kind of depends on Yeah, if you want the characters of compact groups to come from this thing, then you'll need to give it complex arguments. If what you just want is sure polynomials as polynomials, then you can get it from this, but you need to do a kind of exponential change of variable. Basically, this thing will give you the characters, or will give you various families of symmetric polynomials, but as exponential polynomials rather than as ordinary polynomials in n variables. Yeah, so I'll show you a bit more about that in a moment. Okay, so yeah, let's look at some examples. Maybe that'll make things a bit clearer. So in rank 1, the Heckman-Opdam hypergeometric function does indeed just reduce to the Gauss hypergeometric function. So in one dimension, there are only 2 possible root systems. There's BC1 and A1 is a subset of BC1, so we might as well just consider BC1. In that case, we can write the Heckman-Opdam HGF in terms of the Gauss HGF via this formula. Also, as promised, the Heckman-Opdam hypergeometric function does indeed interpolate between spherical functions on symmetric spaces with a given root system in this particular sense. So if we let C be the restricted root system for some symmetric space X minus of non-compact type, then we take V to be this algebra A from the Iwasawa decomposition. We take phi to be this dilation of C by a factor of 2. And for each alpha and psi, we take the value of the multiplicity parameter K at 2 alpha to be half the dimension of the corresponding restricted root space. Then in that case, the spherical function phi lambda minus evaluated at the residue of e to the x is just equal to fk I lambda of x. Now note that here we're only taking x in this subalgebra A, but because the spherical functions are k invariant, we can actually recover the entire function if we just know its values on points of A. So this gives us the whole thing. So with that relation in mind, a natural thing to wonder is whether the same inequality that we posed before actually just passes all the way to the level of Heckman-Opdam hypergeometric functions. So the conjecture is that for any lambda and mu in V, lambda majorizes mu if and only if fk lambda is greater than or equal to fk mu at all points of the space V. So this statement would unify and considerably generalize the majorization inequalities for symmetric spaces. If true, it would immediately imply analogous results for generalized Bessel functions and Heckman-Opdam polynomials. And in particular, it would extend the Cutler-Green-Skandera-Srah inequality from Schur polynomials to Jack polynomials, because Jack polynomials are essentially the Heckman-Opdam polynomials associated to the type A root system. So back to where we started. I originally said this was going to be a talk about the arithmetic-geometric inequality, but I haven't talked about it for about the last 30 minutes. So let's come back down to earth a little bit and bring everything full circle. If we take V to be Rn minus 1, regarded as the space of trace 0 vectors in Rn, and if we take phi to be the An minus 1 root system, then if we take K to be identically 0, these Cherednik operators are just the directional derivatives. The functions gky are just exponentials, and we find that the Heckman-Opdam hypergeometric function is just the lambda mean. And so we precisely recover Muirhead's inequality. So indeed, we obtain the arithmetic-geometric inequality as a special case of this conjecture. Additionally, it's not too hard to convince yourself, if you sort of go back and look at the form of the operators, that if you take k to be identically equal to 1, then what you get is the Cutler-Green-Skandera-Srah inequality. You get it's kind of like exponential version of Schur polynomials falling out. And know that this assumption that all of the x's sum to 1 or sum to 0 is inconsequential, because these means are going to be invariant under translating all of the x's some vector that has all the same coordinates. All right, so as I've said, this is a conjecture. We haven't proven it yet, but we have made some good progress. So first of all, one direction of the conjecture is true. That is, if fk lambda is at least as large as fk mu at all points of V, then lambda majorizes mu. Similarly, by analyzing the classical Gauss hypergeometric equation, this differential equation that the function 2f1 satisfies, we can prove that the full conjecture holds in rank 1. This isn't on the slide and hasn't been published, but actually we can show now that the statement for generalized Bessel functions is true. So the kind of analogous generalization of the Euclidean spherical functions does satisfy a majorization inequality of this type. And finally, the remaining direction of the full conjecture can be reduced to the statement that for each x in the space V, the function that maps lambda to fk lambda of x is midpoint convex. Now, I suspect that this last statement might not actually be all that difficult to prove. And maybe someone watching this can even just see how to do it. I don't know. But what I do know is that the technique that we use to prove the inequality for spherical functions can't work because it relied in an essential way on this integral formula for the spherical functions due to Harish Chandra. And for general multiplicity parameters, integral formulae for the Heckman-Opdam hypergeometric functions are not known. They're known in like certain special cases, but in general, when someone finds a new integral representation for the Heckman-Opdam HGF with some new special multiplicity parameter, it's a big deal, and it's not known for general multiplicity parameters. So some other new technique would be required, maybe using these hypergeometric differential equations or differential difference equations to show this convexity property. So that's where things stand so far. To finish the talk, I want to discuss some possible further directions for this line of research. So one question that I've already mentioned is just, is there an easy proof of the conjecture? Second question is, can these statements be further unified with other results by Cutler, Green, and Scandera on other families of symmetric polynomials that are not known to arise from spherical functions or from hypergeometric functions? Is there something still more general going on that the framework I presented in this talk doesn't cover? And third, if the conjecture is true, does it indicate a still more general majorization principle, for example, for Macdonald polynomials, which are these even more general objects that it is known that you can write the Heckman-Opdam hypergeometric function in terms of. So with this last question in mind, I want to return to the this family tree that I showed you earlier. So in taxonomy, we find a lot of different species, but it turns out that even though they look very different now, if you go back far enough in time, you can find that they all descended from some common earlier species. As a mathematician, I don't spend a lot of time thinking about this family tree, but I do spend a fair amount of time thinking about this family tree. So this is a kind of family tree of special functions theories. This is a figure from J.P. Unger's excellent notes on Dunkel theory. Here, the different boxes represent different families of special functions, and the arrows between them represent either specializations or degenerations, limits. So as we start at some box and go backwards along the arrows, we get more and more general objects. Now, the theorem for symmetric spaces that I showed you in this talk covers these lower three bottom boxes on the left. The generalized Bessel functions that we do now know a majorization inequality holds for live in this box, coming from rational Dunkel theory. The hypergeometric functions of the conjecture live in this box. And so it's natural to wonder whether, if the conjecture holds, it is reflecting some still more general principle that is a kind of a sign of something that's happening in this box or even in this box. So that's all that I have to tell you today. Thank you very much. Are there any questions?
First, let's thank Colin for that great talk. I'm gonna turn off the recording.